It's a cold, blustery day in Brooklyn and apparently in Illinois as well. So we're very pleased that Viktor Todorov from Northwestern can join us today. He's the Harold Hines Professor of Risk Management and Professor of Finance at the Kellogg School of Management at Northwestern, and a fellow of the Society for Financial Econometrics and the Journal of Econometrics. His research interests in the area of theoretical and empirical asset pricing, econometrics, and applied probability. He has indeed published extensively in these fields. His recent work is focusing on the robust estimation of asset pricing models using high-frequency financial data, as well as the development and application of parametric and non-parametric methods of inference for studying risks and risk premia using derivatives markets data. Currently serves as co-editor for econometric theory, is on the editorial board of a number of leading academic journals, including Econometric on the Journal of Econometrics. Received his PhD in economics from Duke University in 2007. And he said he's willing to entertain questions at any point during the next hour. So with all that, please, Viktor, take it away.
Okay, thank you, Peter. Thank you for the nice introduction. And I'm happy to be here. Let me share my screen with you and let's get started. Okay. All right. So today, and yes, as Peter said, please interrupt me during the talk. I would like to take questions rather than wait till the end. So what I'm going to talk today about is option implied semi-martingale characteristics. And what I mean by this is the semi-martingale, the underlying asset price follows a traditional semi-martingale process. And we will try to identify the characteristics of that from the option data. Most and probably the most important of those is the spot volatility. There is the spot volatility or the diffusive volatility. And this is what I will spend most of my time. Probably I will not have time to talk about the jumps, but I think that it builds the idea of estimating and making inference about the jumps will be based on related to the one estimation of the spot diffusive volatility. So in a nutshell, what I will end up with a non-parametric or model-free estimate of spot volatility. And we have already these measures of volatility from option data, most notably the Vix Index. But the Vix Index, as we all know, is a measure of, it's a risk-neutral measure of future volatility. And it contains a lot of, builds a lot of fears, market participants' fears about what can happen in the future. So it's not really a true measure of volatility, but contains also these fear components built into it. And so what I'm going to try to do here is just extract only the spot or the true volatility from the option. And I will be facilitated in doing this by the availability of those short-dated options, or options with very short time to maturity. And so just to illustrate the availability of short-dated options, probably many of you know that, has increased over time significantly. And this chart is just an illustration of this. These are SPX options. And what I'm plotting here is the percentage of total volume traded on, say, CBOE, SPX S&P 500 index options with various times to maturity. And if you can see here from 2011 approximately, when the weekly options the weeklies were introduced by the exchange, you see this gradual increase in these very, very short dated options. And so the weeklies were introduced, I think, around 2011, 2012. And then you have options which are issued on Friday and they expire next Friday. And now in 2016, the exchange also added Mondays and Wednesday expiration dates, like options which are issued on Monday expire the following Monday, and similar with the Wednesday. And as a result, now you have highly liquid options which have like 1 or 2 days to expiration at every point in time. So this type of options, what I'm going to do here, I'm going to make use of the information in these very short dated options. And a lot of this, what I'm going to do here is essentially expansions, short maturity expansions of these option prices. Okay, so as I said, I mean, there are two parts really of this talk. One is about how you make inference about a model-free estimate of this spot volatility from the options. And the other one is about the rest, which is the jumps. And most likely I will not have time to talk about the rest, but we'll see. Okay, and so let me introduce a little bit of notation let me introduce a little bit of notation. So, so the underlying stock price is X, and with capital letters is the price itself, and small letters we will use for the logs. And so it just follows the traditional semi-martingale. We know that from no arbitrage theory, no arbitrage pricing, that we need to have, as the price should be a semi-martingale. There's a little bit of structure introduced here because it's an Ito type semi-martingale, but that I think mostly is a technicality rather than anything serious. And so it's the usual thing. We have a Brownian motion, which drives the stock price, and there's stochastic volatility, sigma t. And then there's this, well, this component here, which is jumps, and which we can't ignore in option data because people's fears are just trying to really put a lot of weight on these jumps. But what I'm going to try to do here is try to make inference for the spot volatility for sigma t, taking into account the fact that there are these jumps in the stock price. Okay, and again, from no arbitrage, we know that sigma t is the same. It's the true volatility. This is unlike the jumps, where the jump measure can be very far from actually the true probabilities of jump arrivals. And so I'm going to try to recover the true volatility from the options. Okay. So now over short intervals of time, what's happening is that this complicated model, and you can have a lot of complicated dynamics built into this. And we know that there's a lot of evidence. People talk about multi-factor structure volatility and jump intensities being very complicated, and in terms of their relationship with the volatility, price code jumps, volatility, etc. But over short interval of time, if I'm looking over, let's say, 1 day to expiration, we can essentially freeze the values of these coefficients of A, sigma, and the jump intensity at their value at the beginning of the interval. And then this model becomes slightly more, slightly simplified, more simplified. And it looks like this. This is just a constant, it's the mean. And then you have Brownian motion, but over a short interval of time, that's just like a Gaussian random variable. And then you have a constant volatility, which we are trying to recover, plus some jumps. And in other words, conditionally on the information at the beginning of the interval, this is a Levy process. Okay, that's a Levy process. And now with Levy process, we can make a lot of progress. There are a lot of known results, and that's what we are going to utilize here.
Yeah, Victor, would you say A0 is determined by sigma 0 and nu 0 here?
Yes, yeah, that's exactly right. So, yeah, that's a good point. So, yeah, A0 effectively, that's right. That's right. My talk is about the semi-martingale characteristics, but the first component of it is uniquely determined by sigma and F and the risk-free rate, which we know. So there's really not that much interest in estimating the A0. The focus is really sigma and F.
Okay, that's fine.
Right. So now, okay, so what we are going to use in the inference, we are going to make use of options, and just let me just introduce the notation for the options. And so the option is O for option, out of the money option, with time to maturity capital T. And I'm thinking of capital T being very small or approaching 0. And so we're using out of the money options, which means that if the strike is below the forward rate, we are using the put, and in the other case, we are using the call. So what happens when time to maturity starts getting closer and closer to 0, when we consider that asymptotic in which we're shrinking the time to maturity of the option to 0? Well, these options are going to lose value, right? I mean, that's intuitive. As you're getting closer to expiration, less volatility, less chance for getting into in the money. But what is interesting actually, and what makes the problem somewhat complicated, is that the way, the rate at which the options are shrinking or losing value is not uniform across strikes. And what I mean by this is that if you look at options which are around the money, which are and I have to actually make one clarification here before I move on. I normalize the stock price today to 1, which means that the lock price today is 0, and which means that the lock moneyness K being close to 0 means that we are close to the money. Okay, so that's just a normalization. So little k being close to 0 means that we are close to the money. We are looking at options which are close to the money. And so if you're looking at options which are around the money, The rate at which they shrink to zero is this square root of t, where t is the time to maturity. But if you look at options which are away from the money, so like 10% out of the money put, for example, then this rate is actually faster, and that's the rate of t.
I think you have sorry, Victor, I think you have an assumption here that all the jumps are like Poisson, as opposed to infinite activity jump processes such as stable alpha.
No,
okay.
no, just a clarification. No, so the result. No, this doesn't depend on this. It's actually for the second result. This doesn't depend. And so maybe let me clarify one thing here. So the result here, the first one, which is around the money, is determined by the presence of the Brownian motion that drives the behavior of the option price around the money. And for the thing away from the money, for the strikes away from the money, that is determined by the big jumps. And so it doesn't matter whether they're infinite or finite activity. Now, the gray area is really for the strikes which are somewhere between, this is a fixed or increasing strike, and somewhere between strike which is shrinking to zero, but kind of at a slow rate. And for those, this activity will start playing a role. So, and here, I mean, the reason why I'm bringing this up here is just that this dynamics of the option surface is very complicated. That's what I want to bring to attention. And so, and we will see a way to kind of get around this and make things relatively simple. But
so when you say fixed, I mean, you probably, let's say, jumps of size 1 or more. Is that what you mean? Yeah. Okay. Fine.
For fixed, for fixed to asymptotically increasing strike. So I keep this. So I'm not changing the strike as the time to maturity is shrinking. Okay. So the strike is. Say I'm looking at 5% out of the money puts, and I'm increasing. Decreasing the time.
Why isn't like strike equals spot a fixed strike? Strike equals current spot a fixed strike.
Yeah. No, that's right. So you can fix it in dollars, right? I mean, the stock price today is fixed, right? So I can fix the strike. I'm not. So what I mean here is that if I fix the strike of the option and I'm having the experiment in which on the same day I'm looking options with say 7 days to expiration, 5 days, 3 days, 2 days, etc. And if I keep the strike fixed, that option will decay.
Yeah, I'm just trying to reconcile the 2 bullet points, because let's say, I mean, I see that there can be a fixed strike, which moreover has absolute value much less than square root of t. I mean, they're not contradictory.
Right. So, that's right. So yeah. Okay. So that's right. So this is not a this is a loose statement, right? So I mean, this is. What I mean by this is that this k is of order, its asymptotic order of magnitude is up to square root of t. And so, but the easiest thing to think about.
And you must mean that the other one is not, right?
Right.
Like the other one is not.
Just to say, okay, the easiest thing to think here, so this is just to provide intuition, but is think of this k equals 0. And so the dynamics when k is equal to 0, if you exactly at the money, this is square root of t. And if you fix a strike, then the dynamics is of order t. You're shrinking at a faster rate.
So if I fix a strike at 0, which is it?
Yes. Oh, if I fix a strike at 0, it's this asymptotic. So it has to be.
Yeah.
Okay. So what is? Oh, I now understand. So this I should have said different from 0. Yeah. That fine.
Okay. Right.
Sorry.
Okay. Now we're in sync. Fine.
Victor.
Okay.
Victor, could I ask a question? As far as the K, I mean, you mean some kind of relative strike. I mean, the units are. I mean, you can't compare absolute value of absolute strike K to T. You're talking about like a relative strike, I assume, right? When you mean by K, right? Let's define some.
So that's what I said is that I normalized the stock price today to 1, and so that's why this is a relative.
Oh,
strike.
I missed that. I see. Okay, so it is the absolute strike, assuming the spot price is 1. Is that what you're saying?
Yeah, exactly. Yeah.
I see. Okay, thank you.
No, I would like I should not create confusion at this point, that early point in the discussion. So yeah, so strike. So this is a log. This is a log moneyness, effectively, right? So it's the distance from the in log terms from the current price. But so you can illustrate this, and I'm sure you have seen probably this. So if you just if you simulate from a basic stochastic volatility model with jumps. And if you if you do that experiment where you just plot the implied volatility as a function of the moneyness, and you look at the different short maturities, you will see exactly this behavior where, so the asymptotics I had in mind here is I keep, say, log moneyness at 0.85, and I start looking at the option price as time to maturity goes to 0. Now this is quoted in implied vols. In implied vols, the things will be exploding as soon as you are away from the money. And at around the money, things are kind of stable and then don't change much. Now, if you want to use one option to estimate the spot volatility, your best guess, I mean, just looking from this plot, I mean, this it's clear that these are nothing. That these values and the implied volatility has nothing to do with true volatility here. So what you would do in this case is your best chance is to use the at the money options, right? And so people definitely have, as I said earlier, an old literature on that. So you can use the Black-Scholes implied volatility at the money, okay, or very close around the money. And when you do that, I mean, when time to maturity shrinks to 0, that will recover the true volatility. So in fact, this expansion is relatively, which you see here on this slide, is relatively simple to do. It's relatively straightforward, and I think that Nasdaq has this now, this type of based on this relationship as an estimator of the volatility index constructing, which you see here at the bottom. You just use the at the money option, multiply by square root of 2 pi, and then you get the volatility estimator. Now, however, you have this error term here, and this error term comes from the jumps, from the presence of jumps. And now, how big is that term? Well, if you look at again, I use simulations and realistically calibrated model option pricing models, which we have estimated in previous empirical work. And so the blue line on this plot here is the true volatility, because I'm simulating from the model, so I know exactly what the true value of volatility is. And the dashed line is the at the money Black-Scholes implied volatility generated within the model again, but from options which have 1 week to expiration. So these are quite, I mean, relatively short time to maturity options. And if you see the gap, I mean, even with at the money Black-Scholes implied volatility, it is quite elevated relative to the true volatility. And what is even worse, if you want to make this as your estimate of true volatility, is that this gap between true volatility and that Black-Scholes at the money implied volatility is time varying. And it increases a lot in periods of crisis, and then it shrinks. And so just the dynamics are somewhat different, not to speak of the levels. So then you kind of, well, you can ask, then you can say, well, maybe, yes, this is a nice it's a nice theoretical result, but it is just a theoretical result, and there is nothing else to do about this. But but alternatively, one can say that, well, I mean, if we have so many other options here, although I know that these options here are not that informative about the true spot volatility, but we can try to utilize all options across all strikes to extract the spot volatility. And so this is the second approach I will follow here, and we will see that it will lead to a great improvement on a relationship on an estimator of spot volatility from these options. So the idea is very simple, and let me just talk about this. So we are going to use this result from Peter's earlier work, where what is known is that you can recover in a model-free way the risk neutral expectation of any smooth function of the terminal price. Okay, so X capital T. And so this is, again, on the left-hand side is something which we don't know. And on the right-hand side, we can actually, you see, we have an integral against the strike or the log strike, which involves the option prices. And so in practice, if we have a lot of strikes with options with a lot of different strikes, we can actually approximate this integral here by a Riemann sum. And so the same thing is used in the Vix index, right? In the Vix index, you have a specific formula. You have here f being the log function, and that gives you the Vix. But of course, we can apply it with a lot of different functions, not just the Vix is one particular function, and we will apply it with different functions. And so now, knowing this result, now I can cast the problem which I'm trying to solve here in the following way: design or choose a function f, which will allow me in the best way to separate the volatility from jumps and just to identify the true spot volatility from the data. And now based on my previous work in high frequency asymptotics, I'm a little bit in a more familiar ground now, because we have been doing a lot of this type of work in that field, and designing these functions where you can separate volatility from jumps. And so two candidates are to use the what I will call like a smooth truncation. So you look at the function x squared. So you're trying to calculate, say, the return variance, but then you truncate it in a smooth way, multiplying with this exponential. And you see, when eta is very high, what you're doing is you're truncating, and you're truncating really the big moves. Okay, and the ones which are very close to zero, you are leaving barely unchanged. Okay. And so if you start choosing eta high and higher as your time to maturity is shrinking, then you can asymptotically at least separate the volatility from the jump. So this is one way, but I found that way is actually less efficient than the second way. And the second way, which I will follow here, will be based on the characteristic function. So the the function e to the power iux, which will allow me to recover the characteristic function of the return over that interval of time, or the stock price. But again, we are conditioning on the initial price. Those two are equivalent. Okay. And so if I write it on the next slide here more explicitly, this is the formula, right? It's a very easy thing, right? I mean, this, you don't need much work. I mean, this is a very specific formula. It gives you the characteristic function. It gives you an estimate of the characteristic function of the return. Okay. And now, because time to maturity is short, the process is conditionally Levy, approximately. And then I can use Levy-Hinshin theorem. And that's what I stated on the last part here of the slide. So now everything is nice. All the three characteristics are showing up here. So you have the drift term here, you have the volatility, and you have this last piece, which is because of the jumps. So if I look at,
yeah, sorry, no, can you explain why you're dividing by square root of t?
Yes, no, that's right. That's important. So because I mean, if I think, let's think about in the simple case when there are no jumps. And so let me see where, if there are no jumps, sorry, I have to go all the way back here. So if there were no jumps, and then this piece is basically, this piece here is gone, and then xt is sigma 0 times wt, but that means that in law, it's square root of t times a normal. And so when I divide by square root of t, I normalize and everything is on the same scale, it's not shrinking, right? So if xt over square root of t will be always normal, regardless of what t is. And so that's what that normalization is, just putting the things on a scale where nothing is shrinking and nothing is kind of as I get closer to exploration. That's the natural scale. Basically, because of the self, how is it called, that the scaling law of the Brownian motion, right? So that's the reason for the square root of t. But now, if I go back here, sorry, to this flipping now. Okay. Oh, that's not the right time to. That's really okay. We're back. Okay. Remind me later. I guess I always do the same thing, and that's why I keep being reminded. Yeah. Okay. So back to this. But okay. So you see, here is the volatility, and then this is the stuff about the jumps. And so now, if I look at the real part of the log characteristic function, the drift is automatically gone. I'm left with the volatility and a little, well, it's not little, but and a piece from the jumps. So now let's just zoom in a little bit and look at this. And so what is happening here? I expressed everything here. So if I use the log of the characteristic function divided by u squared as my estimate of volatility, then it will be the true thing up to that term, which is written in blue, which is about the jumps. Now, nice thing about cosine is that it's a bounded function. And so if jumps are finite activity, like the most typical
Yeah,
case,
that's what I was saying before.
yeah. So if
Right.
jumps are finite activity here, then this integral is a bounded function. And in that case, this term here is of order t. So that actually is.
So I agree with that statement. What if they're not?
What if they're not? Now, if
Yeah.
they're not, what will happen here? The measure f0 is exploding, and so you need to and it's exploding around 0. So what you have to do, there are nice inequalities about the cosine function, and so what you will do is let's say that the jumps, the activity of the jumps is measured by this index r, which is that's the Blumenthal-Gettor index of the jumps, but in intuitive terms, what r is, it tells you how fast is the Levy measure around 0 exploding, right? And so, okay. And so again, r equals 0 corresponds to the finite activity jumps. R equals 1 corresponds to finite variation jumps, and so on and so forth. Okay.
Yeah.
So now in this case, what you have to do, you will have to tame a little bit that measure f0 because it's exploding, and that will lead to this bound. It's t to the power 1 minus r over 2. So now, still, I mean, if I compare now the two estimators here, so remember, I started with add the money, Black-Scholes, implied volatility, and then I'm looking at this alternative characteristic function-based estimator volatility. This is the two error terms. And when r is equal to 0, which is the most typical case we have in applications, then this is of order t, this is of order square root of t. Now, if r is higher, when r gets to 1, then those two are the same. I should make make clear here that an assumption which I have made is that r is below 1. So I'm not allowing infinite variation jumps. And if I allow for infinite variation jumps, this bound is also not correct here. So the bottom line is that this contains a far less bias than the Black-Scholes add the money implied volatility. And it's a more efficient way of separating volatility from jumps, which is really not that surprising if you view this from the point of view of if you view this in the context of the analysis, which I told you here, picking the optimal function which separates the volatility from the jumps, it actually will be a miracle if the Black-Scholes, the money implied vol, will do exactly the job. But just I want to, before I move on, just to give you the intuition. I mean, the intuition is very simple. If there were no jumps, so that piece is gone here, right? I mean, I'm looking at the characteristic function of a normal variable, or normal random variable, and that's the characteristic function is e to the power minus u squared over 2 sigma 0 squared. And so in that case, that's my estimator is just I transform that characteristic function into volatility. And so in the case of no jumps, that estimator is exact estimator of volatility. When there are jumps, this estimator is going to tame them if you pick u high, so that the higher the u, the smaller that number here is. So asymptotically, so theoretically, it does a better job than Black-Scholes implied vol. How does it do empirically? Of course, because I mean, that might be just an kind of a nice theoretical result. It's not, and so I'll have more to say on this as we proceed. But here's one illustration of this. So what I plotted here is, again, everything is within simulations, right? Just because I know the true volatility in simulations, and so I simulated on a given day. I simulated. So on a given day, I calculated from the model the option prices with 5 and 7 days to expiration. So the blue line is 5 days to expiration. The dashed line is 7 days to expiration. And then I did exactly this calculation, which is I calculated this characteristic function portfolio from the option data. And then I made this transformation. So I took minus 2 over u squared, the log of this characteristic function portfolio. And what you see here plotted is this as a function of u. Now, the horizontal line here is the true volatility. So this is rather a variance. So that's why you have to square root it to get to the annualized volatility. So this is 0.02. Square rooted, this is approximately 15–16% annualized volatility, okay? And what is happening here is that as you as you pick U higher, that estimator gets closer and closer to the true volatility. Now, one thing which I should point out, if you notice here that if U is equal to 0, they start at the same point. And what is this point? Well, if you take the limits, all of what I did here was for U different from 0. But actually, if you take the limits when U goes to 0 of this function, then it's not difficult to show that what you are recovering here is the Vix. Okay, and so you start with the Vix at U equals 0, which is total volatility, which includes the jumps. And as you start increasing U, you are actually robustifying or kind of getting rid of these jumps, which I know that they actually have nothing to do probably with the truth, because it's risk premium kind of, mostly it's risk premium, this risk neutral jump variation. Okay, and so when you go U high, you're going to recover the true volatility. Now, so, I mean, you might ask at this point, why not take U goes to infinity? The problem is that if U is very, very high, empirically that estimator will become unstable, because the characteristic function for very high values of U will be very noisy. And we will see it. I will show you how you do this on the data. But it's very, so what you do in reality, what you'll do in practice is pick the U corresponding to the value of the absolute value of the characteristic function being somewhere like, say, 0.2, 0.3, something like this, relatively low value, but not really that close to 0. And then that separation of volatility from jumps will happen.
So just to understand this graph, I know the blue curve is the characteristic function based estimate of volatility, and what's the black dashed curve?
So both are characteristic function based estimators, but they are with different times to maturity. So the blue line corresponds to 5 days, and this one corresponds to 7 days. So obviously you have an easier, for the same U, you have a better separation of volatility from jumps with the short dated options, right? The closer you are to expiration, the better you separate those things.
Thank you.
Easier time to separate. No, I mean, it's not mentioned on the graph, but now in reality, of course, I mean, this was all nice, but in reality, we will have, we have a finite grid of strikes, okay? Now, I don't expect this to be a problem, just like it's not a problem for the Vix index. So I don't expect the finiteness of the strike grid to be an issue. And you will see that this is not an issue. Here, observation error, that can be a problem. But luckily, as you will see later on the plots, most of the weight of this estimator, quite intuitively, is from at the money options. And so if those are relatively precisely recovered, or we have precise data, that's not going to be an issue. And then the time variation, so I mean, obviously I froze the characteristics here, and you know, like you can have variation of volatility over very short intervals of time, like volatility spikes and things like that. Again, this, for the models I have simulated from, it tends not to be a big deal. But if you're worried, there are ways to actually remove this type of potential biases by doing, by using the different maturities and kind of scaling and differencing in certain ways. So I just empirically, my observations that this is not so. It's not so.
So Victor, why do you? I mean, you're writing you have error due to presence of jumps in X, but I thought you accounted for presence of jumps in X. So
right. So I mean, well, but what I mean is that, I mean, there's something remaining, right? Even if you choose.
Oh, okay.
There's a little bit remaining.
And finite U. Okay, that's fine.
Yeah, finite U. Yeah.
Okay.
Yeah. So now, I will go quickly through this, because I mean, this now going from continuum of strike grid to a discrete strike grid, that's kind of trivial what's happening here. You will replace the integral with the Riemann sum approximation, or using a trapezoidal rule or something like this. That's not that difficult. And there will be observation errors. I need to allow for that, because in the data you see the kind of across neighboring grids, neighboring strikes, you can have the option price kind of jumping around. So we do allow for that, okay? And then your estimator becomes, again, it's very simple. I mean, this thing is like 2 lines of code to apply, and then you have the volatility estimator based on this, right? And then There's more theoretical results in the paper, so I don't want to turn this into a theoretical discussion here, but you can characterize the rate of convergence. You can also even derive a central limit theorem, which allows you to quantify how much, like a confidence interval, how confident you are in that estimator of volatility. In the interest of time, I will not talk more about this, but there's interesting interplay between the coarseness of the strike grid and the closeness to the time to maturity, etc. So they do show up here in these rates. So if you're interested, this is in the published paper contains that the formal discussion of this. Now, instead of going through these formal results, what I want to show you here is how you do it, and this is the data which gets into the calculation. So what I plotted here is just an arbitrary day in my sample. This is January 16th, 20th of January, January 2016. So the options, this was on a Friday, I believe, and then they had exactly five business days to expiration, these option prices. So what I plot here is out of the money option prices. And so around 1850 is the current stock price. And so everything to the left is out of the money puts. Everything to the right of 1850 is out of the money calls. What do you see? I mean, you see, we have so many strikes. It's actually amazing how many strikes are available on that index, on the S&P 500 index on that day with 5 days to expiration. You also see the huge asymmetry. I mean, you have from 1850, you have out of the money puts going all the way down to 1500, and then calls going to 2000. So that's that just reflects the asymmetry, or this big left negative skew, the negative skew which we are all familiar with. Okay, so you use this option data here, this out of the money calls and puts, and you enter them into this formula, right? You enter them into this formula. You choose U so that the characteristic function takes a value of approximately, say, 0.2 or 0.3, something like this, like a relatively low number, but not very crazy low. And then you calculate this portfolio, which is here, again, I restated here on the bottom of the page here, right? That portfolio, this is a portfolio of the options. And again, chosen for this relatively large value of U. And so now what I plotted here, I wanted to, I split the portfolio in the real part and the imaginary part of that portfolio. Now remember that according to the theory, the value of my estimate of volatility is coming from the real part of this characteristic function here. So I can focus on this on the left plot more. What I plotted here is the contribution in this portfolio, which determines the value of the spot volatility of each of those options with the different strikes. And so what you see here, what is happening here is quite intuitive, I think, is the highest weight is assigned to at the money options, and then options which are close to the money also receive positive weights, but they are kind of fast declining. And then you see that portfolio goes short some of these options around 1800 and then 1950, something like this. And then effectively, as soon as you move more than 2 standard deviations away from the current price, the weight you assign to these options is 0, which is also consistent with our intuition that these options around deep out of the money options contain no useful information for the spot volatility. And so that's exactly what this estimator is doing, is just shutting them down in the portfolio formation. In fact, you can show in the theoretical results that you don't need these out of the money options. You can throw them away, and so everything will still go through. But effectively, that's exactly what you're doing in the construction of this portfolio, which is zeroing them out. And so you have that kind of a long short type portfolio where the short part is relatively small, but you can view it as a bias correction, in fact, for the effect of the jumps. Now, also, again, if jumps are shut down, and so over short intervals of time, the only reason for asymmetry in the return is because of jumps. There's no leverage effects and things like that. Then, so if I have picked U very high and jumps play a negligible role, the imaginary part of that portfolio should be equal to 0, because again, this standard normal is centered at 0, so there's no asymmetry in this. And so now that's a way to test whether this is true. So look at the imaginary part of this portfolio. What is it doing? It's going long out of the money calls, but near the money, and short out of the money puts. But you see the way it's doing it, it's like assigning approximately the same weight on the calls and the puts. And the calls and the puts very close to the money are actually symmetric. I mean, so if you look at this function here, it's very close to being symmetric around the zero. And so as a result, when you sum all of this up, they cancel out the long and the short part, and this becomes close to zero. Okay. And again, the intuition for that is that you're gathering the information from very close to maturity, close to the money options, and around which are dominated by the diffusive part, which is symmetric. And so the symmetry of the option prices around the money, or approximate symmetry, ensures that this imaginary part of this characteristic function portfolio is close to zero. Okay, now let me show you a little bit on the data. How does it behave on the data? Okay, so we calculated this. On the, again, S&P 500. We have done it with individual stocks, and in fact, I have some empirical work on that. And so what I plot here is the following. So the black line is this characteristic function base estimate of spot volatility, and the red circles are the estimates coming from returns. Now, how do you do this from returns? From returns, you take squared returns from the data, but over a local window. So here, I'm observing these options at the close of the business day, and so I use a local window, like say of like 5-6 hours, and I sample very frequently, like every minute or so, something like this, and then I calculate this return-based estimate of volatility. So what you see is that the option-based estimate of volatility is on average at the same level as the return-based estimate of volatility. But of course, what you can also note is that the red dots are way noisier than the option-based estimator. So that's the whole point of this here, is that you get a much more precise estimator of the volatility compared to the return-based estimators. And in fact, estimation of spot, this is one of the reasons why I went in this direction here, because estimation of spot volatility from high frequency returns is notoriously difficult. You have very imprecise results. Some people will call this utopia, that you can recover spot volatility from returns just at this level of precision. And I mean, and the noisiness in the red dots is just illustration of that. But the point here was that as a level, you are getting your estimator exactly as the true volatility is. And this is something, this is unlike the Vix Index. We know the Vix Index is way elevated relative to the true volatility. Now,
can I jump in?
Yeah,
got a question.
Yeah.
So, like let's say a view is that the return-based volatility is the P volatility,
right,
and the option-based volatility is the Q volatility, which in theory is the same as the P volatility.
Exactly.
That theory assumes no arbitrage. Let's say there is arbitrage. Then let's say this suggests the possibility of doing trading on the view that, the options market is somehow not perfect. And, is there any sense of whether,
Yes.
trading a mismatch would actually be profitable?
Yeah, that's a good, that's an interesting direction, actually. Yes. So, I mean, you can actually, what you can do also, to do that kind of thing, it's a great idea. And so I will put also confidence intervals around my estimators, because, like there's measurement error and stuff, but the good news is that you can do that. And if something is really out of the bounds, yes, I can, you can think of something of that nature. But I'll be a little bit cautious, because the way I kind of I already mentioned, the reason why I went in this direction is that when I was doing a lot of work in this high frequency field and asymptotics field, and then I noticed that there are quite a few days when just the return-based estimate of volatility just gives you some very crazy data. And this is the days when you just cannot trust very much the return data, that there's something which is happening on this price discovery, slow price discovery, things like that. And it's just the volatility you get is just gigantic, and it's nothing to do with the truth. And so so these are the periods when you have this kind of big deviations. Now, whether you can arbitrage this away, I don't know, maybe you can, but
yeah, I mean, let's just say theoretically that, let's just say that the options market actually is very good at thinking about jumps, but maybe is somehow bad about thinking about the volatility you're after. And so you're trying to just trade that volatility that you're hoping the options market misprices, and you're presenting a way to get a pure bet on that volatility, which is the position in the at and near the money options, and actually, very interestingly, somewhat short the slightly away from at the money options. So that's interesting. Like, let's say nobody I've ever seen suggested trading volatility that way, and so it's worth exploring is all I'm saying.
So yeah. Okay, yes, but yeah. Okay, so maybe we can talk a little bit more afterwards about this. But I wanted also to zoom in on 2020, because 2020, I mean, if you want to test anything in terms of volatility estimator, that's probably 2020 is your year, because we started with extremely low levels of volatility, and then we shoot it up to extremely high levels of volatility, and then the market start gradually decreasing. The volatility start gradually going down, and then there were again spikes. So it's really a perfect laboratory for for doing that analysis. And I think that estimator performs, from my point of view, amazingly well in tracking this dynamics. And so you see it's very close in the middle of these red dots before March of 2020, and then it matches even in these extreme high peaks, and then again on the way down, it's still tracking it very well, except that you can see that the red dots are all over the place, right, above and below. So there's just a lot of error, but that thing is just getting it very close. And more of that, a little bit of advertising. We created an index. We created a website. Let's see if it will work in real time. So with Torben Anderson, who is my colleague in Kellogg, and so we have measures of the TEL index, and we also have that volatility index. So it's just it's a comparison here we are running with the Vix Index, just to give you an idea. So this is over a longer period of time, from capturing also the financial crisis, and then you will see these kind of periods of gap between the VIX and the true value of volatility expanding and shrinking, and that just captures all these kind of fears of people varying over time. Okay, so we are probably So in some work, I also did this on a bunch of individual stocks and stuff. This is just purely empirical to illustrate the gains from doing this. Now, I don't know whether I should talk about this, but one thing here is like, I can go back to one of the classical problems of, classical quote unquote problems in this option-based versus return-based volatility in this, at least in the academic finance literature. And so which one is better, the option-based or the return-based volatility estimator? And so you can put it in a context of volatility forecasting, which a lot of people kind of care about, and so so you can do that, and then in interest of time, I mean, like, yes, the answer is not surprising given the plots I showed you. You really improve a lot. It's actually the improvements, the order of magnitude improvements are kind of impressive given the fact that how much this literature is relatively mature, I think, in terms of kind of the best forecasting, volatility forecasting models, and you can still improve a lot on that. Now, I have a couple of more minutes left, so I'll just give you the idea. What about the jumps? And the jumps are now a more complicated thing. way more complicated thing. But so what I'll be interested now, as Peter was saying, well, if that jump measure is infinite, then of course it doesn't make sense to be recovering f of 0, the measure, the jump compensator or the jump intensity, or which counts how many the expected arrival of jumps of given size. But what you would like to do is recover the second moment or truncated second moment, right? Because that thing is guaranteed to be finite. Okay, and so that's the natural thing to recover here. And so what in a way, what I will try to do, I will try to recover the tails, right? So for an arbitrary value, a threshold var theta here, that's the Greek var theta. And you can view this as I'm chopping the pieces of the Vix index. So I'm slicing the Vix. The Vix contains the spot vol, which I recovered, and then it contains this jump piece, and I can start cutting the pieces of that, of the Vix index in kind of in the tails. Now, how do you do this recovery here? Well, I mean, it's a very simple kind of via Fourier inversion. You can just relate these tail integrals with the characteristic function of this transformation of the Levy measure, where you multiply by x squared, right? I have to multiply it so that I dampen the measure around 0, so nothing explodes. Okay, and so there's this simple relationship. So it's relatively simple. That's like just, I don't want to recover the density itself of that because that's a little bit noisy. So that's why I focus on the tail integrals. And it's just people mostly interested in these tail integrals. Okay, and now let's come back to the characteristic function portfolio. So everything is coming from this characteristic function portfolio. And so again, if you remember, the characteristic function approximately in this Levy approximation has this form. This is the Levy-Hinchin formula. And now I'm interested in this.
Well, can I ask, is U here real or is it complex?
Yeah, it's complex. U is a complex,
okay.
So it's an arbitrary complex number. Sorry,
okay.
All right. I have to switch to that. Sorry, yes.
Okay, yeah, fine.
Yes. And so now what you do, if you take the second derivative, of the log characteristic function, then what you will notice is that what you recover is the characteristic function of this characteristic function here of the jumps plus the spot diffusive volatility. And so then that's it. What I need from here on is I have an estimate of the log characteristic function portfolio. I have an estimate of volatility that will give me the characteristic function of the modified jump measure. And I will do the Fourier inversion. That's essentially what you will do.
I mean, an issue I expect you discovered when you did this to data is that your estimate could be negative. Does that ever happen?
The estimator of you mean the jump iteration?
Yeah. So like it's not supposed
because because I stopped things. You're thinking because of this centering here?
Yes.
No, but okay, so here's how I do it actually. So there's a few subtle points here, because the natural thing which you will think here to do is to use my optimal estimate of volatility. By the way, I didn't mention, but there's a theoretical work which shows that the estimator I showed you of the spot volatility is optimal in a minimax sense. Okay, so or rather, I should say almost optimal. Okay, almost optimal. So that you can't do much better theoretically than that. But it turns out that here, and this is I was a little bit surprised by that, but turns out here that it's not optimal to use the optimal estimator here, volatility. Rather, what you should use is you should use the value of this function evaluated at a very high level of U, because that is also an estimator of volatility. It's not an efficient one, but it does a cancellation of the weights you assign to at the money options or around the money options. It cancels in the portfolio here and this estimator here. So it's a little bit subtle, the argument here too. And so I probably don't have time, but in any case, just to say what you need for all of this to work, you need your Fourier transforms to be decaying when U goes to infinity. And that will be always the case if the functions are smooth. And so by smooth, we have to assume that the levy density, well, first of all, the levy measure has a density with respect to Lebesgue, and then that density is, say, continuously differentiable. So that kind of, so you need some kind of a smoothness. So if I have, say, jumps of a fixed size, and so I assign a mass on that's not going to, that's clearly not going to work. So you need a little bit of smoothness in the levy measure. So by the way, this is something that you don't need for the spot volatility estimator. So here for the jumps, you need a little bit more structure. I think it's minimal, but nevertheless, you still need it. And I illustrated here with tempered stable, or rather Carr-Geman-Madan Yor process. And so you can, we just don't have the details for that. But again, the final estimator here is that you center with the value of the character, the second derivative of the characteristic function for that high level of U. And the estimator is.
And can you prove that? I think that's a good idea. Can you prove that the resulting estimator is necessarily positive? I think you might be able to.
I think I never. That's probably, I should think about that. But I never experienced any issue of that.
Right.
Empirically, so that's why I probably didn't think of this.
Okay.
But yeah, okay. You're right. I mean, that's something that it's probably should be. Yeah, because that's is that guaranteed to actually be positive? I think actually it's not guaranteed to be positive, but
okay.
I experienced So
okay.
Now this is here. Let me not spend more time. I mean, you can show the asymptotics, but I'm really getting out of time. And so now you can. What I did here is. I estimated, well, we have the spot volatility, and then you have a tail measure, which is by tail measure here, I estimate, say, the volatility, which comes from 5 standard deviation negative downside move. And then I plot also the blue line is the total negative jump variation. And so you will see the dynamics, well, I mean, everything, it's a little bit, lines a little bit stretched because you have the crisis period in it. That unfortunately here I didn't include the 2020 here and that on that data, but we will include that too. And there are subtle differences in these dynamics. That's all I can say here in the interest of time. But the tail part tends to be a good signal about the stock market behavior in the future. So it's a good predictor of the returns. And that's not the case, or not completely the case for the spot volatility. You also see that a lot of the return variation is generated also by small jumps, and that's also an interesting observation coming out of this. Okay, let me conclude with this. So this is again, this is about model-free measures of volatility, jumps variation, etc. And it's based, I think, on a very simple idea. You just build a characteristic function portfolio. It's a portfolio of options. If you want the diffusive volatility estimated at a high value of the characteristic exponent, and that gives you an estimate of the volatility. For the jumps, as you see, you need a little bit more work. It's more complicated than that.
Okay. I just comment that a motivation for this latter part on jump variance is corridor variance swaps. I don't know if you know what they are, but these are over the counter. Okay.
Yeah. Can you? Yeah.
Yeah. So these are over the counter contracts that pay variance only while you're in some region, and so let's say people would be interested in
corridor, like a corridor type thing.
Yeah.
Okay.
Yeah.
So, okay. That's interesting. Okay. So I didn't know. So they're over the counter. Okay. Isn't like on SPX and things like this.
Yeah.
Okay. That's very useful. Yes. That's right. So this will be exactly this type of thing. Yes, because this is it's slicing it into these regions. Yeah, that's right.
Yeah. So just in terms of making use of all the data, let's say it sounds like you're focusing on the short end of the term structure. And I'm thinking that, if you have calendar spreads, you can also be using longer maturity options, by calendar spreading 2 maturities, you're in principle picking up
because the calendar spread should be a short, so the gap between the 2 maturities should be small, right?
Correct. Yes, that's exactly what I'm thinking. And then a different point is that, you know, you can also like use the longer dated options as a way of trying to extrapolate towards the shortest maturity. So in other words, like, let's say you're thinking, you know, let's use 2-day options, and that's fine. But let's say implicitly, you're not going to use the 4 days, but I'm saying use both the 4 days and the 2 days in an effort to get towards 0 days.
Yes. Yes. Okay. That's a very good. Yes. Okay. Thank you. Thank you for mentioning this. Yes. I actually, I have a follow-up work here, and that's exactly
Okay. What you
that,
did.
that's
Okay.
exactly going in that direction. That's
Yeah.
exactly.
Okay. Okay.
Yes.
Fine.
And you can get it. You can. I think that the as incremental contributions, I think it contributes a little bit and improves on that one, but the improvements are not that big, I think, but it improves. Yes, that's right. So you can make it, yeah. I mean, now it's really beautiful because you have like 2, 4, 6, 7,
Yeah.
8, etc.
You should use them all. I agree with that. Yeah. Yeah. Okay. Okay.
That's a
Great.
great point.
Okay.
Steve Figluski here.
Oh, hi, Steve.
How are you doing? Very interesting talk, very interesting idea. I wanted to make sure that I understood some aspects of it. It seems to me you're using high frequency data. You use a whole day's worth observed at very short intervals, a minute or a couple of minutes at a time. But in your estimation, you're assuming that the 3 elements, the diffusive volatility, the jump size, and the jump frequency are constant within the day. And then tomorrow you do the same thing again with a different day. And from your pictures, it seems that there's, you know, a fair amount of variation from day to day in these things. I'm interested in what you know about how much they might vary within a day, and also what is it, you know, what are we learning about how much these things change from day to day? It seems like this is a very volatility process.
Volatility. Okay, so that actually, okay, so you're bringing up very interesting points here too. So yes, now you have to remember that is true. So what I'm assuming is that in these derivations, what I'm assuming is that volatility just let's forget about the jumps. Volatility stays constant over a course of a day. Okay. Now what I should have mentioned is that what you need to assume only is that volatility. So if you have deterministic changes in volatility during the day, that's okay. Everything goes through too. And so if you are worried, say, for this big intraday diurnal patterns in volatility, where volatility is high at open, low at the middle, and then very high at the end, so everything will go through what I did here. So as long as it's just a deterministic, and this is largely a deterministic pattern, so everything will go through. Now, second is you have to remember that the options, they are expectations, and that's right. So they can be changing, but the relative weights assigned to this time varying part is just relatively small, and so as a result, the expectations are not so much affected by it. Now, as I mentioned in answering Peter's question, yes, what you can do is exactly you can expand the characteristic function and you account for this time variation in the characteristics, and by using different maturities, you can kind of cancel those components too. And so to effectively what Peter was saying, is to achieve like a day 0 type of volatility. So
I like that idea. That was clever, Peter.
Yeah. And so now, what the final thing is, yes, we have estimated this. So what I presented here with the option estimator is only using the data which is in option metrics, which is end of day, but we also purchased some high frequency option data. And so we estimated the volatility from during the day using this approach. You tend to see more or less flat lines. So it's actually not that much movements in volatility, surprisingly. Once you account for that diurnal pattern, that actually volatility doesn't change that much, which also tells you that there's a great benefit from aggregating all that intraday option data information. But and one can study all sorts of properties of volatility, which we kind of could not. And I know that people. Some people are very excited about this rough volatility modeling. Well, that's kind of, I mean, if you want to study roughness of the path, that's what you want, right? The spot volatility, because it gives exactly this higher frequency variation. And so that's just a perfect tool, I think, to do that. But thank you. That was a good point. Yes.
Okay. All right. Well, thank you, Victor. That was very interesting work, I must say. It sounds like you're continuing with it. So thanks. We've been trying to get you to speak here for more than a year, and I'm glad we finally made it happen. It was due to the pandemic, things got mixed up. But anyway, we much appreciate the presentation, and look forward to seeing more work along these lines. Okay. All right, we can wrap it up. Abby, you can stop the recording.
Yeah.
Thanks, everyone. Okay.
Thank you.
All right.
Bye.
Thank you,
Bye.
yeah.
Bye.